Hello everyone for watching my talk. My name is Thomas Kupfer and I'm a new faculty at Texas Tech University. Over the next 10 to 15 minutes I would like to give you an overview of a dedicated survey to find compact binaries which can act as verification systems for LISA and present a new type of a greeting system which will have a detectable gravitational wave signal in LISA. But before I go into much detail, let me first remind you where we stand with LISA detectable compact binaries. So in 2018, uh, we published a list of objects, of systems, uh, accreting systems, detached systems, which are expected to have a strain, or signal, a gravitational wave signal strong enough to be detectable for LISA. This list is very inhomogeneous. There are currently 16 systems known. Most of them are accreting systems because they're just easier to find in electromagnetic wave bands. And this is a very inhomogeneous sample. It's not really a good representation of LISA should see or will see. And we really wanted to change that, to find more systems, but also to find them in a much more homogeneous way. And because these systems are so compact, they will actually show variability in their brightness, in their light curves on the orbital period, just due to eclipses or accretion or deformation of the components, which are caused by tidal forces. And what we wanted to do is to repeatedly observe the sky and to look exactly for these brightness variations on the orbital period. So here are examples shown of eclipsing systems where you see this drop in brightness, or deformations where you see these additional variations on the orbital period. And the telescope, the machine we used for that, is the Zwicky Transient Facility, also known as ZTF. And this is a telescope built or located on Mount Palomar, which is just 2 hours south of Los Angeles. And it's a 1.2 meter or 48-inch telescope, which is equipped with a very large field of view camera, which allows to observe a large fraction of the sky repeatedly over hours, over days, very often, to really look for these brightness variations. And in particular, for these kinds of systems, we built a survey dedicated to find these compact binaries, which LISA will see when it flies. So we built a survey which was really dedicated to that. And so what did we do? So first, we looked at the sky position of potential candidates. So we were looking mostly at potential white dwarfs or potential helium stars. And we were looking where they are on the sky, where are the candidates. And that's basically the sky plot in the upper part of the slide. You see this yellow blue area, and the yellow area is where the density of these objects is the highest, and that's around the galactic plane. Overplotted are these orange and red squares, and these are actually the fields we selected to observe, to find these systems. And so what did we do to really specifically look for these systems? Because these binaries we are talking about for LISA have periods of less than an hour, so really tight. What we did was we went to a specific field, and then we repeatedly observed the same part of the sky for a few hours with 40-second cadence. So every 40 seconds we took an exposure for a few hours continuously. And the idea really was to look within these few hours blocks to look for short period variations which could be caused by a compact binary which will be seen by LISA. So we covered a large fraction of the sky. Actually, in total, there were a few 100 million stars which we covered. So that's quite a challenging job to really bring down to the numbers of manageable sources to look for these. So what we did was we basically took the data from a field, which you see here. So we selected one field. The upper right, you see this one particular field here. This field has 5 million individual stars, just this single field. So then what we did was for each of these objects, for each light curve, we calculated statistics, like variability statistics, for example. And then we plotted them, and then we really look for the variable objects. So you see this in the lower right. Again, this colored area is where the stars are. It's a density plot. And then the lower red curve is basically the median of, in this case, something like a variability median versus the magnitude. And then the upper red line is the 3 sigma limit above which we would call things variable. So we find about 5% are potentially variable sources over the course of hours. So that is still a high number, but much more manageable than really looking at a few 100 million objects. And here I'm showing one example where you see the star is actually the location in this variability plot, and then on the left-hand side you see the light curve over 1.5 hours, and you see this is actually a source where we observed a few cycles with this repeating pattern of this deep and less deep minimum. And I come back to this in a second, but it really is a challenging job to go from these few 100 million sources down to a manageable number of sources to find the interesting ones. And just to give you a little bit of a glimpse of what we found, it really turned out to be a treasure box. There was tons of interesting stuff there. This includes a new type of pulsating star, which you see in the lower right, which is not seen before, with periods of 3 to 8 minutes, but also LISA background sources, which you see in the lower left as an example. That's a white dwarf with a brown dwarf companion in an 80-minute orbital period. But we also found LISA sources. You see the upper left, that's a new double white dwarf with a period of 24 minutes. And we also discovered an entirely new class of accreting systems, which you see in the upper left. That's a helium star, which has started to accrete on a white dwarf, in this case with a period of 39 minutes. So that's what's showing here, really these. The way we really could extract that was that much deeper minima is when the accretion disk is moving in front of the helium star. And with an orbital period of 39 minutes, that puts it right in the regime where it's interesting and potentially interesting for LISA. And then it's a helium star with a white dwarf companion. And just as a reminder, that's not the first one which might be seen by LISA. In 2018, when we published this paper where we had all these systems, we had one of them already on there. That's CD-30 up there. That's a helium star with a white dwarf companion, but it's just detached. It's at a much longer period, but it's much closer. That's why it's really also high enough signal-to-noise ratio in LISA that we will see them. And particularly these helium stars with these white dwarf companions are interesting as candidates for type 1a supernova progenitors, where the helium star donates onto the white dwarf and the white dwarf just blows up. These are important for binary evolution, so basically just how to make these binaries. And they are very bright in electromagnetic wavebands. Some of them will be seen by LISA, so they are very interesting for multi-messenger studies. And in particular, this new system, which I showed, this object with a period of 39 minutes, turned out to be particularly interesting. So we did a lot of follow-up, a large follow-up campaign. We took light curves, we took spectra, we measured velocities, and we really put all the pieces together. And we found that this is actually a rather low mass white helium star with a very typical white dwarf companion. And if you put all the pieces together, you find that this object in particular will have a signal-to-noise in LISA of a roughly 5 after 10 years. So it's not great, but it should be able to be being detected. And because we have this beautiful data in the electromagnetic wavebands, we really be able to do multi-messenger observations and really combine, for example, then the trip mass from LISA with the masses we measure here, and then really get much tighter constraint of individual system parameters, which makes it then interesting to think about the future evolution of these kinds of systems. Interestingly, that's not the only system of this type, even though it was the first. There's another candidate now. It has a very similar light curve shape. The follow-up spectra, follow-up data look very similar. And this one is, in that sense, even more interesting because we see a weak eclipse of a hot white dwarf in there, which lets us put constraint on the accreting white dwarf. And we find it's a very hot white dwarf, which is exactly consistent what you predict for the accretion rate the models say that this system should have. Unfortunately, this system in particular is at a 2 kiloparsec, has an orbital period of 56 minutes, so that won't be able, that the signal noise in LISA will be very low, it's around 1, so it's very, very hard to detect. But in general, this is really now consistent with a new class of binaries where helium star has started already to accrete onto a white dwarf, which could actually be the missing link of type 1a supernovae coming from where helium stars accrete onto the white dwarf reaches a limit, and then actually blows up. Some of them, if the period is already tight enough, if they are not too far away, they will be seen by LISA with a signal-to-noise ratio good enough to do multi-messenger studies, because all of them, if they are close enough, they will be very bright in electromagnetic wave bands, and they're therefore very ideal sources. And to really just finish up at this point is in a study led by Ilva Göttberg, and I really encourage you to watch her talk. We predicted the numbers of helium stars with white dwarf or neutron stars companions, and we actually found that a few tens of them could have signal-to-noise ratios high enough that LISA can detect them, and then all of them will be bright enough in electromagnetic wave bands, and we really can do multi-messenger studies and really put down the numbers of how many sources there are, what are the masses, are they good as type 1a supernova progenitors or not. And so this is really exciting times for these systems, and a potentially really interesting class of stars LISA could see when it's flying. And with that, thank you very much for your attention, and feel free to email me, contact me if you have further questions or want to discuss further points. Thank you very much.